Hey, Matthew, how's it going? Fair enough. All right, so all right. I don't have much to say about associativity because there is a huge gap in between us being able to prove it and what you know, and that gap is called linear algebra. So I'm going to tell you the theorem that lets us prove the other theorems, and then I'm going to move on to some other interesting series things. Um, yeah, I wish I could prove it, but literally we need like 2 years of algebra foundation to do it. So yeah. Bacharach. Let me see if I spelled it correctly. Um, is this what it is? No. Oh, Bacharach. Okay.
All right, hi.
Hello. So let's say we have three cubic curves, C1, C2, C3. And these cubic curves, two of them, if we take two of them, they intersect in 9 points, counting multiplicity. All right, so with the cubic, let's call these points P1 through P9. What this theorem says that is that if our third cubic curve passes through P1 through P8, then it must go through P9. So this seems like a very surprising result, I guess. Surprising is a good word for it. Let's see if I can draw an example. Or you know what? Well, no, I'm not going to try to draw an example. This is just a very powerful result, which requires a lot more math than we can kind of gloss over. But so how does this help us in Pappus's theorem and Pascal's theorem? All right, so first thing actually I should say is that notice the product of three lines is technically a cubic curve. And the product of a line and a conic is a cubic curve. So let's open up GeoGebra, new share. Let's see, maybe I have this already. Okay, so let's just remember how Pappus's theorem worked. So let's actually sort all of these so that I just got to do that. And then let's make these. Here, let's just get rid of that. Call this one A1 and then A2 and then A3.
Hello, Corbin?
Hey, Ashworth, how's it going?
Yeah, sorry, I'm a little late.
It's all right. So I unfortunately am not going to be able to completely prove associativity. I am going to tell you what you need to prove it though. So let's see, color is red. Okay, and then what I want to prove today, if we have time, or in the future, if we can't get it done today, is I want to prove that the factorial of 1/2 is equal to the square root of pi divided by 2. Have you guys ever heard that before?
No, I haven't.
I have.
How would you even prove something like that?
An infinite series. I'm not entirely sure how factorials of fractions work.
Yep. Well, hopefully we will be able to show the magic that is the gamma function.
And also, oh yeah, you gave us a choice in what we were going over today, right?
Uh-huh.
So I think Ashton and I agreed on this. Can we learn the integration techniques?
Yeah, integration by parts specifically. Because
Okay.
like we weren't really like taught much of it in actual calc.
And also,
Yeah.
it's very
Seems-
powerful.
It seems pog.
Great. Well, I was hoping that you would say that because that is the lesson that I prepared for today. So
That is indeed fog.
I'm surprised you're in the spring semester of Calc 1 and you haven't seen integration by parts yet.
We're actually done learning things. They said we're gonna start reviewing for the calc test now.
That makes my brain itch, but all right. So Ashley, let me just catch you up on something that we're definitely not going to prove. It's called the cubic Cayley-Bacharach theorem. So suppose we have 3 cubic curves. In general, 2 cubic curves would intersect in 9 points, counting multiplicity. And so let's call those 9 points P1 through P9. Then the theorem states that if the third curve passes through the first 8 points, then it has to go through the 9th point. And then you should notice that the product of 3 lines is a cubic curve, and the product of a line and a conic is a cubic curve.
Wait, does it mean like if cubic 3 passes through all like 1 through 8 or just like any one of them?
It has to pass through all 1 through 8.
Okay.
All right. Oh, that's the wrong one. Open up this one. All right, so let's go back here. So these 3 red lines, that's a cubic curve. These 3 blue lines, if you multiply them together, that's a cubic curve. And we can see that they do in fact intersect in 9 points, right? Maybe this one and this one should be changed into purple. That was the purple that I used. And then we can color these, we can make these thick black. Okay, so we have 6 purple points and 3 black points. And so if we pick one more black line, the product of the 3 black lines is also going to be a cubic curve. And since the black line, the third black line passes through A and B, let's say, then the cubic Cayley-Bacharach forces it to pass through the 9th point. Does that explanation make sense, assuming that the cubic Cayley-Bacharach is true? Like, do I need to elaborate more?
Could you?
This is so hard. So yeah, if here, let's just go to this. So like let's say I have Li is equal to the equation AIX plus BIY plus CI is equal to 0. Then the product L1, L2, L3 is we're going to say A1X plus B1Y plus C1 times A2X plus B2Y plus C2 times A3X plus B3Y plus C3 all equal to 0. If you expand that out, you would get something that at first glance wouldn't be obvious that it factored into a product of 3 lines. And but it's technically a cubic curve, right? So that's why I color coded these things in the cubic Cayley back or in the Pappus's theorem here. So we start with 2 black lines and we pick 3 points on both of them. And then we did that alternating red-blue construction. And that gave us 3 more intersection points. So the product of the blue lines is a cubic curve, and the product of the red lines is a cubic curve. So if I make a third line that passes through A and B, then and I multiply it by the other 2 black lines, then we have a cubic curve that passes through A1, A2, A3, B1, B2, B3, A, and B. So the cubic Cayley-Backrack theorem says, oh, that cubic curve has to pass through C. Does that explanation make sense?
Yeah, it does.
Yeah, the way you said in products was better.
Okay. So let's see it again for Pascal's theorem. Don't save. All right. So we're gonna need some variables A, B, C.
Corbin, it's okay if I leave for a sec. I'll be back in like 2 minutes.
Go for it. Whatever you need to do. All right. So we have A, X. Oh, here, let's put a point. Let's force it to pass through this one. Okay, so we have ax squared plus 2bxy plus cy squared is equal to a x of a plus, oh, that should be squared, plus 2bx of a y of a plus cy of a squared. And there we go. Here, wait, let's make this a compact conic. Positive, put it to 0. There we go. All right, so we got a compact conic. Now let's pick 6 or 5 more points on it. And we got to relabel them. Say this is A1, B1. Oh, that didn't save. A2, B2, A3, B3. So if you're interested in a proof of the cubic Cayley-Backrack theorem, you should definitely start studying algebraic geometry. All right. But at the very bottom of algebraic geometry is linear algebra. and abstract algebra. So let's make that red, make that blue, make that red, make that blue. All right, and let's move these points around so that the intersection points are more visible. Got this one. We got this one. Okay, all right. So again, the three red lines multiplied together make a cubic curve. Oh, wait, I don't want to intersect. That's the tool. And let's see, this one here, and finally these two. So if I draw a black line through A and B, the product of the black line through A and B, of the black line with the conic is a cubic curve, which passes through the first A points, A1 through A3, B1 through B3, and A and B. So therefore, it has to pass through C, according to the cubic Cayley-Backrack theorem. So we're going to assume that the cubic I have to also explain the line at infinity. You guys don't know projective geometry either. It's that dang linear algebra again. All right. So maybe one day I will teach you guys projective geometry, which is a very, very beautiful and important theorem or field entirely of just geometry. But I kind of need some setup to explain what a line at infinity is and how you would multiply a line at infinity by an equation to get a cubic curve, which you can do, but it's going to need some work. So this is what you need to study to get to associativity. One day you should just have a huge multiple hour lecture. You just teach us everything. Yeah, one day I need to have a huge multiple hour lecture where I teach myself everything, because there's still so much to do. All right, so let's talk about integration techniques for getting certain series. So we used integration by parts to define a Taylor series. Like at the end of the day, we really want these Taylor series. This is the foundation of modern science, basically. And so we were able to get the series for e to the x, cosine of x, sine of x, cosh of x, and sinh of x. And actually, there is one Taylor series that everyone learns way before they ever touch calculus at all. So let me just remind you that the Taylor series of a function centered at r, some number r, is the series from n equals 0 to infinity of the nth derivative of f evaluated at r divided by n factorial times x minus r to the n. So let's just verify actually that this is a Taylor series. So first of all, what's the derivative of 1 over 1 minus x?
Itself. Or not itself, but it's like it's 1 plus 2x plus 3x squared. So it's like factorial. What?
ln of 1 minus x?
It is 1 over 1 minus x squared. So we could use, and actually that is what you would get here if you use the product rule for multiplying series. But let's just use the power rule. There's no reason to overthink this derivative. We can rewrite it this way. And then according to the power rule and the chain rule, it's equal to that, right? And actually, it's kind of a fun exercise. If you remember the way that we got e to the x, we started with this differential equation, e primed equals e, and e to the 0 equals 1. I guess I should write this, yes, dx primed. This geometric series here actually satisfies the differential equation f primed is equal to f squared and f of 0 is equal to 1. It's a fun exercise to solve it that way. Okay, but let's keep going. So what's the double derivative of 1 minus x, or 1 over 1 minus x? Well, it's the derivative of this thing. So I'm going to rewrite it like this. Minus 2. So the...
So 2 times 1 minus x to the negative 3.
Yep. And what's the triple derivative?
6
6
times 1 minus x.
1 minus x to the negative 4th.
All right. And what is the nth derivative?
N factorial 1 minus x to the negative n.
Negative n in minus 1?
Right.
Yeah. So that is, we said that was 6 over 1 minus x cubed. So at all of those, if we just plug in x is equal to 0, then we get n factorial, right? So d to the n of dx to the n of 1 minus x to the minus 1 evaluated at x is equal to 0 is equal to n factorial. So the n factorials cancel with the n factorials in the denominator of the Taylor series. R is equal to 0, so we just left with x to the n. So that's an example of a Taylor series. So this is a really small list of special functions though, right? I'm pretty sure that you should be familiar with this special function. Here, let's move that line down a little bit. Oh, it's doing that thing. It's not letting me erase. Okay, there we go. Okay, so this special function, the natural log of x. Let's say it's equal to y. So I want to find a series for this function. So, and it's going to be, there's going to be a lot of integration involved, don't worry. So, but the way that we've been finding these series kind of follows where we first set up some sort of like differential equation for this function that we wanted to satisfy, and then we use that to find the series. So let's take care of that. So this is going to be defined by this equation. E to the y is equal to x. So therefore, it better have these properties. Ln of a plus ln of b is equal to ln of ab. And ln of a to the b is equal to b ln of a. So these are familiar properties, but we just need to make sure it has these. We're going to use these. So let's start with just one fact about E. I'm pretty sure your high school teachers have already introduced E as this limit. X over u. So if we set u is equal to hx, then we get that h is equal to u over x, and our limit becomes the limit as h goes to 0 of 1 plus hx to the 1 over h. So we're going to need this. It's a special tool we'll use later. So now we can actually compute the derivative of the natural log. That's the next thing we want. So we want to prove this. Well, actually, does anyone know off the top of their head what the derivative is? We're going to prove it, but
1 over x.
correct. Did you guys get a proof of this in your calculus class?
We did not.
What are they doing? They're wasting your time. Okay, so we're going to say that the derivative of the natural log of x is equal to the limit as h goes to 0 of the natural log of x plus h minus the natural log of x over h. So then, according to our natural log rules, if this thing is going to be the inverse function of e to the x, then we better have that this is equal to the natural log of 1 plus h over x all to the 1 h to the power. Now, since e to the x is continuous, which we didn't prove, then its inverse function is going to be continuous, which we also haven't proved. And since it's continuous, we can move the limit to the inside, which we, again, haven't proved. So we get that this is the limit as h goes to 0 of 1 plus h over x to the 1 over h. But if we look at this definition of the exponential function as the limit, we can see that this is actually e to the 1 over x. This is the natural log of e to the 1 over x. But we're saying that the natural log of e to the a is going to be 1 over x ln of e. And these are inverse functions, so this should just be 1 over x. Great, great. So this is a proof where we've glossed over a lot of small details. So we have d dx ln of x is equal to 1 over x. So that is the same thing as saying, according to the fundamental theorem of calculus, that the integral of 1 over x, let's say from, is equal to the natural log of x plus some constant. So let's use this. Actually, I'm going to do the definite integral. I changed my mind. Say 1 to infinity. So do I want to do it that way? Let me look at my notes. Can't even find it on my notes. I did it like twice last night in 2 different ways. Why is it not here? Oh, there it is. Let's do the indefinite integral. We can just find c at the end, because we're going to have the condition that ln of 1 is equal to 0. So we'll be able to find c. So there was a reason that I brought up the geometric series earlier. Let's rewrite this as 1 minus 1 minus x dx. Do we want to do it this way? Let's do a u substitution, actually. Let's say that u is equal to x minus 1. So that x is equal to u plus 1. Dx is equal to du. So we get the integral du over 1 plus u. And this is equal to the integral, I guess I can write that right here, of n equals 0 to infinity of minus 1 to the n u to the n. Yeah, that looks correct to me, du. So again, we're skipping all of the details about convergence and continuity, but since the natural log, or since 1 over x is uniformly convergent, we can switch the integral and the sum sign. And so if this was a finite polynomial, that wouldn't be a problem, but this is not a finite polynomial. So we have to worry about things like that. But at the same time, you're high school students, so you don't have to worry about things like that. When you get to real analysis class, then you can worry about things like that. So we can just integrate term by term. So we get -1 to the n, u to the n plus 1 over n plus 1, which is equal to the sum from n equals 0 to infinity. Oh, we have a plus c right here as well. Yeah, there we go. Do not forget the plus c. So, what? Come on. Why is it lagging? I made sure to charge this before class. Okay, so we have this. I'm just gonna restart it. It's struggling. Oh, there we go. Now it's smooth. So let's rewrite this as C plus. I'm going to raise the index by 1 so I can lower this by 1. So we get -1 to the n minus 1 u to the n over n from n equals 1 to infinity. And then I'm going to replace u back with x minus 1. So we get c plus n equals 1 to infinity minus 1 to the n minus 1 times x minus 1 to the n divided by n. Great. So we need to find c, but we are insisting that the natural log evaluated at 1 is 0. So we're going to get 0 equals c plus n equals 1 to infinity minus 1 to the n minus 1, 1 minus 1, n, but all of these are 0 terms, so c is equal to 0. So then one thing that I didn't mention, we use the geometric series here, so we're going to have to make a restriction on the size of u. So if the absolute value of x is less than 1, then the natural log of x is given by this formula where it's centered at 1. So this is a Taylor series at 1. So we have x minus 1 plus x minus, no, sorry, that should be a minus sign. Yep, minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4, and so on. So yeah, you should always be thinking natural log whenever you see an integral like this. So I'll give you a minute to ask any questions if you want before I move on, if you want me to elaborate on anything. All right.
Yeah, well, sorry.
Go ahead.
Can you hold on? That summation thing. Up again. Yeah, the du over 1 plus u. That's just because of convergence, right? It converts into that integral because it converges.
Yes. Yeah.
Okay.
So there's a lot of subtlety around when you can flip a sum sign and an integral sign, or a sum sign and a derivative sign. But if your series converges uniformly, then you're good. Then it doesn't matter. But there is a lot of wacky things that you could do with series that don't converge that end up not making a lot of sense. Like for instance, if you plug in the right values into the geometric series formula, you get that 9 plus 90 plus 900 plus dot 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 equals -1. Maybe there's some sort of information that could be have sense be made out of that, but for now, we're gonna just insist on you have to check convergence if you want to use this to build a bridge. If you're just doing math to see some really interesting and mind-popping patterns, then we can cool it with the tedious stuff like convergence. So the next thing that I want is, so I did the natural log because it's a good example of the next thing that I'm going to do. And our goal here is we want to prove that 1/2 factorial is equal to the square root of pi divided by 2. And we're going to do that in 2 different ways using 2 different integration techniques. But in order to do that, we're going to need to know a certain integral. So does anyone know how to integrate this bad boy? So this is our sub goal, I guess. This is probably an integral that you would see on the Calc 2 test, but it's not that hard to prove. It's more just like the pacing of the topics. So this thing is actually equal to arctan of x plus c. And we're actually going to use this integral to get a series for arctan because, you know, that's kind of just what we've been doing. And this series does converge everywhere. This is a nice integral. But for now, let's start at the beginning and just ask, what is the derivative of arctan? So d dx of arctan of x. Well, let's start with arctan of x. It's equal to y. And that's actually the same thing as saying x is equal to tan of y. And this thing is going to be a lot easier to take the derivative of. So if we take the derivative of this, we get 1 is equal to, what's the derivative of tangent? Does anyone know? This is a good exercise to do. Yeah, I'll wait for someone to do the quotient rule for me. Let's see.
X squared, right?
Secant squared?
Secant squared, yep.
Yes, x squared.
Yep. So cosine, sorry, 1 over cosine. This is how I've been writing it. Okay, so we have secant squared of y, but according to the chain rule, we also have to multiply this by y primed, which is the quantity that we're after. So we get that y primed is equal to cosine squared of y. So this is a differential equation that's definitely nonlinear. But the thing about this differential equation is it's telling us something about trigonometry. So we can use that to get over the difficulty of otherwise solving this differential equation. So if we set this equal to y, and so tangent is sine over cosine. So let's set this equal to x and this equal to 1. According to the Pythagorean theorem, this is 1 plus x squared. Why are you doing that? Okay, and so we get y primed is equal to 1 over 1 plus x squared. And that is the same thing as saying the integral of dx over 1 plus x squared is equal to arctan of x plus c. All right, I actually do not want to go over time. Okay, great. We have 20 minutes. Awesome. And so this is a good exercise for you guys. Just a homework exercise. Find derivatives of arc cosine, arc sine, arc hyperbolic cosine, and arc hyperbolic sine. And for these two, you might want to keep in mind that cosh squared minus sinh squared is equal to 1. That's a very fun exercise to do. And if you are able to do these, then you will at least be able to compete in some integration Bs in the future. So let's find a series for arctan. Technically, this is the only the integral that I needed, but let's find a series for arctan. So we can rewrite dx over 1 plus x squared as a dx over 1 minus negative x squared. So this is equal to the integral over k equals 0 to infinity of it's going to be minus 1 to the k x to the 2k dx. So arctan has the nice convergence properties that let us flip the summation and the integral. So we're integrating minus 1 to the k x to the 2k dx. So this is equal to the integral from k equals 0 to infinity of minus 1 to the k x to the 2k plus 1 divided by 2k plus 1. And then we have a plus c. So what we know that arctan of 0 should be 0, right? So if we plug that into here, then we get that c is equal to 0. That's pretty nice. I will say that arctan is one of the few inverse trigonometric functions that has a nice series like this, or that you can use a geometric series for. If you were doing arc cosine or arc sine, then you're going to need to know Newton's extended binomial theorem, because you're going to have a square root in the denominator. But that's a really nice series. And it's extremely useful. It comes up all the time. This, or I should say, actually, this integral comes up all the time. This is definitely one of the integrals that you want to know right here. All right, so I think we're only going to have time to do the gamma function one way. So next time we will finish up the gamma function using more interesting techniques that are also really powerful. And right now, today, we're just going to use integration by parts to study the gamma function. Oh boy, I might not be able to prove this today, that 1/2 factorial is equal to the square root of pi over 2, but we can get close. That square root of pi is an indication that there's an arctan integral involved. So let's just look at this random integral, 0 to infinity of x to the n minus 1. Let's call this integral gamma of n, x to the n minus 1 e to the minus x. Let me just triple check that I'm not messing this up, because I have done these computations a few times in the past 24 hours and made mistakes every single time. So yep, dx. All right, so we're going to define this thing to be the gamma function, and let's just see what happens when we do some integration by parts. So if I set u is equal to x to the n minus 1 and dv is equal to e to the minus x dx, then we get that du is equal to n minus 1 times x to the n minus 2, and v is equal to minus e to the minus x dx. All right, so this integral is equal to negative x to the n minus 1 e to the minus x evaluated at 0 and infinity. And then we have minus, we have another minus sign right here, so that becomes a plus. The integral from 0 to infinity of n minus 1 x to the n minus 2 e to the minus x dx. All right, so here I'm going to wave my hands a little bit and say that, well, if we plug in 0 for x, then we're going to get 0 minus. Here we have the minus sign. I'm going to factor out to the outside. Now, I'm just going to say that e to the minus x goes to 0 faster than x to the n minus 1 blows up as you're taking the limit to infinity. So when you plug in infinity to this thing, you're going to get 0 again. So what we have shown is that gamma of n, which is equal to, let me just state it again, this integral x to the n minus 1 e to the minus x dx is equal to n minus 1 times the integral from 0 to infinity of n minus 2 e to the minus x dx. And what do you notice about this thing? This thing is actually gamma of n minus 1, right?
Yeah.
There's something pretty profound about this integral. So if you were just to do like some sort of interpolation of the factorial operation, then you would find a bunch of different possible functions that would assume the same values as the factorial. But this is the nicest function that satisfies this functional equation. And we never made any restrictions about n being a natural number. This just holds if n is not a negative integer. And the reason that it breaks when n is a negative integer is because this thing can be infinity over a positive number when you plug in 0. So we don't want it to have any poles, or we don't want it to be infinite anywhere. So that's the only restriction. This integral will happily tell you what the gamma of 1/2 is. So is this the factorial function? Well, we have gamma of 1. Let's see what that is. That's going to be integral from 0 to infinity of x to the 0 is 1, so I'm not going to write it, e to the minus x dx. This is equal to minus e to the minus x evaluated from 0 to infinity. If we plug in infinity, then we get 0. So this is equal to 0 minus, if we plug in 0, we get 1, so it's equal to 1. So gamma of 1 is equal to 1, and gamma of n is equal to n minus 1 times gamma of n minus 1. By induction, what we get is that gamma of n is equal to n minus 1 factorial if n is natural. But again, this integral makes sense for anything that's not a negative integer. So let's put this to work. If we are interested in what is 1/2 factorial, then we can say, I'm going to define it to be 1/2 times gamma of minus 1/2, because this integral is actually way easier than again equals, it's much easier than this one. So I'm going to use easy in air quotes again because there are two different ways to do it, and versus the one way that I know how to do this. The two ways that I know how to do this are pretty interesting, and we only have 10 minutes left, so I think I'm going to end with this. And so let's find out what gamma of -1/2 is. So gamma of -1/2 is equal to the integral from 0 to infinity of, sorry, that shouldn't be -1/2. That should be just 1/2. Sorry, regular 1/2. Please let me, okay, that's good enough. If it's just gonna draw, that's good enough. So we have positive right here, 1/2 minus 1 e to the minus x dx. So this is equal to the integral from 0 to infinity x to the minus 1/2 e to the minus x dx. So as it stands, this thing looks pretty ugly. So let's do a u substitution. U is equal to x squared. So du, no, sorry, other way around. U is equal to u, x is equal to u squared. So dx is equal to 2u du. Or we could say that dx over 2 is equal to u du. So let's rewrite this thing. Wait, let me get this out of the way. Let's move this over here so I have more space. X is equal to u squared. Dx is equal to 2u du. So we have this integral is going to be the integral from 0 to infinity of u e to the minus u squared du, and then we're going to have a 2 on the outside. This is where I confused myself several times. That's not a u, that's a u to the minus 1. There we go. And dx is equal to 2u du. There we go. There we go. So we have u du here. So that's equal to 2 integral from 0 to infinity e to the minus u squared du. All right, so if you had a little more experience with calculus, you would look at this thing and you would throw your hands up and you'd be like, Corbin, why did you make this a harder integral? This is known as the Gaussian integral. And it comes up a lot, notably in probability. It is a lot in probability and Fourier analysis. So, all right, I am going to integrate it in a sort of not the interesting way that is a integration technique that works for a lot of different things. I'm going to integrate it in the way that you will probably see if you were just sitting in an engineering class, or I saw it in my partial differential equations class, but you might get it in Calc 2, honestly, as well. So no, it would probably be Calc 3. So first I need to tell you how to do integrals in polar coordinates, and you'll see why. No. So let me do this thing. So we just need to find the value of this Gaussian integral. So I'm going to rewrite it again in terms of x. So we have, oh, it really doesn't just want to let me write. Okay, so the integral from 0 to infinity e to the minus x squared dx is equal to the square root. Again, it kind of looks like what I'm doing here is just making it stupider and harder, but this is all so that we can use polar coordinates to integrate this thing. So all I've done is I've multiplied it by itself. And since this thing is strictly positive, we don't have to worry about taking square roots. So now let's talk about regular or polar integrals. So let's say I have a polar function like this. If I want to integrate it from here to here, we have to worry about the angle that we're making, the infinitesimal angle, whatever that means, and the radius. So if I have an integral like this, some f of x, y, so sorry, some f of x squared plus y squared dx dy, that's equal to this new integral, f, let's say just g, some no, never mind. It's equal to f of r squared r dr d theta. So you have to put this r here. There is a way better explanation for why when you do this change of coordinates, you have to put that r there, but I'm just going to draw a hand wavy picture. So I guess I'll keep that up. So let's return back to this integral here. 0 to infinity, e to the minus x squared dx, integral from 0 to infinity, e to the minus y squared dy. Since the first integral is completely independent of y, we can rewrite this as integral from 0 to infinity, integral from 0 to infinity, e to the minus x squared time plus y squared dx dy. Basically, I'm just pulling the integral to the side, pulling the dx to the other side, and then combining the e to the minus x squared, e to the minus y squared. So I'm sorry, this is the most unmotivated part of it. We're going to do it a better way with a different integration technique after this, but I just wanted to show you two different ways to do it. And this is also the way that is very common. This is what a lot of people do. Also, this is just like a warning to never, when you get to Calc 3, Calc 2, whatever, and you're doing polar integrals, never, ever, ever, ever forget the r. It goes from dx dy to r dr d theta. So, however, we have now an x squared plus a y squared here, which puts us in perfect position to replace that with an r squared. So if we think about where we're integrating from, we're integrating over the whole first quadrant, right? So in polar coordinates, we have an angle of pi over 2, and the radius is from 0 to infinity. So our new integral is 0 to pi over 2, integral is 0 to infinity, e to the minus r squared r dr d theta. And the whole reason why this is beneficial to us, why we would want to do it this way, is because now we can do a u substitution. If we say that r squared is equal to u, then 2r dr is equal to du. And so we get a new integral, 0 to pi over 2, integral 0 to infinity, and then we have a 1/2 e to the u du d theta. So e to the minus u, there we go. So if we plug in infinity, this is 0. Oh, where's the minus sign going wrong? We don't want to have a minus sign in here. Should I say minus r squared is equal? Let's see if we do it that way. Then we have, oh boy, all right. Then we have the minus sign out here. No, we definitely need that minus sign on the inside. Right here. I'm sorry if I'm going to make you a couple minutes late to your next thing. Let me just see if, oh, no, never mind. Why am I doubting the process? It's going to work just fine. It's going to work beautifully. Okay. E to the minus u, 0 to infinity d theta. So at infinity, this thing is 0. At 0, this thing is 1, but we're subtracting it. So the minuses cancel out. So we get pi over 2 to 0, 1/2 d theta, which is just equal to pi over 4. So if we go all the way back up here, we have this Gaussian integral is equal to the square root of this thing. So we get the integral from 0 to infinity of e to the minus x squared dx is equal to the square root of pi over 4, which is equal to the square root of pi over 2. And then we have 2 times, if we were asking what is the value of gamma of 1/2, that is equal to twice the Gaussian integral. So we get, come on, why are you doing this to me? Load back up, please. There we go. So we said that gamma of 1/2 is equal to 2 times square root of pi over 2 equals the square root of pi. And 2 factorial, or 1/2 factorial, is equal to 1/2 times gamma of 1/2 is equal to square root of pi over 2. So we didn't use the arctan integral for this method. There is a much cleaner method that doesn't use the polar integration to do this. And I know we covered huge amounts of ground today. So I will take any questions about anything that we talked about. I'm sorry for all the hand waving.
Yeah, no, I feel like the only parts I don't get is just why it's not rigorous.
Yeah, it's not rigorous, but it still gets the right answer. The only reason that we would care about rigor in this instance is if we were building a bridge, but we're not building a bridge and we're not dealing with any wild sums that do crazy things. So the rigor isn't the only part where I'm upset about the hand waving is when I switch to the polar integral to do the Gaussian integral, but that's fine. On Wednesday, we will see how to do this without polar integration in a way that lets you solve a bunch of other integrals as well. And we're also going to prove that the gamma function has that integral is the gamma function without using integration by parts, because I also waved my hands there to say that infinity to the n is smaller than e to the minus infinity, and so therefore it was 0. That we don't have to do that either with the next method that we're going to learn. So yeah, I'll make sure to send the video to this because it's quite a bit. I do have to get to my next class though, so I'm going to bid you guys a good afternoon.
All right.
All right.
How about
Bye.
good afternoon?
Later.